the way we generate our energy in 20 years and especially and particularly in 40 years. So you see on the full portfolio side, by 2030, you're essentially nuclear and renewables with coal waiting to get carbon capture and storage on it. And then by 2050, you're renewables, nuclear, and carbon capture and storage on coal, essentially. So it's essentially highlighting the difference in our future based off the decisions and the investments that we make over the course of the next decade. So we really are at quite an interesting time from our economy perspective and particularly from our energy perspective. So here's from the economic side now. This just goes to show the cost of investment. So you can see when you're not investing in new technologies and you're not investing in the R&D, of course the limited portfolio ends up being substantially more expensive from a cost of energy perspective. But what you're also seeing is even with the investment, cost of energy is almost doubling. We're getting an 80% increase even with this full portfolio. So that's really the need. That's kind of really what the end story is within 40 years, if we're going to hit these needs, or if we're going to hit these targets, in order to prevent some of the issues that we'll discuss, we want to accept the fact and recognize the fact that it is going to cost us something. This is from a GDP perspective now. So essentially taking a limited portfolio, this is another way of saying the same thing. From a limited portfolio perspective, we're taking net present value essentially of the cost of all these infrastructure changes on the economy. It's a little over $3 trillion GDP impact from a net present value perspective. And then there's the second bar there is decreased hit on the GDP because you're allowing the advanced efficiencies, advanced renewables, but we're stopping CCS and nuclear. And then on the full portfolio, this is essentially advanced renewables, advanced efficiency, and also you still have carbon capture and storage and nuclear as well. Another caveat to note, this doesn't take into account the potential cost of doing nothing based off the impacts. So that's a question that often gets asked about this is, what about the cost of doing nothing to the economy? And we haven't taken that into account. We haven't analyzed that here. So this doesn't address that. The real kind of meat of this is that in the limited portfolio, or between the limited portfolio and the full portfolio, those are technologies that we can do. I mean, we know we can do them. We've already assessed the potential for them. They don't exist today, but they can exist with general R&D. But what we really need to decrease the cost to our society and make sure that we can make these changes happen is innovation from universities, from students, from startup companies, from national labs, from other research organizations. We need innovation to make sure that we're able to make the changes necessary to minimize essentially the economic cost of making these changes within our energy system. So I'd like to jump quickly now to our PRISM 2.0, essentially this next generation. It's essentially recognizing the fact that the one-size-fits-all approach doesn't really make sense from a technical perspective. So PRISM 2.0, as it's been dubbed, essentially taking a regional approach, so that way you can take advantage of regional energy resources, particularly associated with renewables and other energy sources that are available, as well as the transmission associated with those regions. As I'll mention in a second, transmission is also a major issue when it comes to electric generation. So I'm going to give you one kind of, this study is still in development, so I wish I could speak to the solar aspect. I'm going to speak to the wind, a glimpse at the wind study that we've looked at, but some of the learnings definitely carry over with variable resources. So essentially, when you look at wind in the United States, you have essentially all of the wind that you could ever want is right where none of the people really are. So the biggest problem, of course, is getting all of that wind if you're going to take advantage of the wind, is getting that to the population centers, which are primarily on each coast. Important to note also, there's enough wind in the Great Plains states to power the entire country. No sweat. It says we have identified 5,300 utility scale sites of over 100 megawatts. So that's well above our total generation and total electric demand in the entire country today. The difficulty, of course, is using that and making use of that energy. And also taking into account the fact that it is a variable resource. So this is just, engineers may get a kick out of this, but essentially this is the big challenge when it comes to variable resources. This is the big challenge for solar as well and other variable resources is that, so what we've done here, we looked at 50 gigawatt capacity of wind, and this is over the course of a week. So we installed this near a population center, and over the course of 2 or 3 days on the left-hand side, with the max per year near 50 gigawatt capacity, that marker, what you're seeing is essentially for 2 or 3 days, all of your electric needs are covered by the wind. So any other plants or backup facilities you have are off for those 2 or 3 days. But just 2 or 3 days later, a high pressure system comes in, the wind stops, there's a heat wave, and the wind literally stops blowing, and your turbines essentially spin down. So now you need to have some sort of backup power, because the biggest thing about energy, particularly electricity, is that when we flip on the lights or flip on our projector, it needs to turn on. The system needs to be reliable. So that's the big challenge when it comes to, and the big opportunity really, when it comes to integrating renewables and integrating variable sources, the fact that we need to figure out a way to cover the gap between the red line, which is the demand, and the blue line, which is our wind energy resource. Whether it's storage, whether it's peaker or natural gas plants that we can kind of turn on and turn off very quickly and run for a set period of time. Whatever it may be, we need to figure that out, and we're making investments in that with regard to smart grid storage, and then also those advanced generation technologies from natural gas and other plants that you can turn on and off. That's one of the biggest things also, is with our existing grid, our generation, our bulk generation really isn't made to turn on and off. It's really made to turn on and run. So coal plants, nuclear plants, and even some gas plants, essentially they're on nearly 24/7, 365. So if you're talking about now turning them on for 2 days at a time, turning them completely off for 2 days at a time, and turning them back on, just to be able to counterbalance the wind resource, the variability, you're going to need to make some changes to the system, and there's some real need for innovation and real opportunity to develop new technologies in that area. Similarly, this is not quite the case with solar, but with wind definitely is. Biggest problem with wind is that it likes to blow at night, which is right when we don't need it. So at nighttime, as you can see where the blue line's getting pretty close to the red line, again, the blue line is the wind generation, the red line is the demand. You can almost cover your demand with wind, but it just happens to be that right when everyone starts to turn the lights, air conditioning starts to turn on, then your wind energy starts to die off. And again, you need to fill that gap. You need to find technologies, find some generation technology to be able to fill that gap. So this is, again, going back to the fact that there's so much wind available in the United States. This is essentially looking, and cheaply available actually, this is based off the generation cost. What you see on the bottom axis is the amount of wind capacity there is, and then on the y-axis going vertical is what you have, is what you see with the cost of electricity. So it's actually relatively cheap to get quite a bit of wind if you were just talking about generation costs. But now you have to bring into account, and again, sorry for the eye chart, but you take into account the fact that transmission isn't there and there's not a way to get it to the load center. So what this is essentially showing is the need for the cost effectiveness and the need for transmission if we're going to be developing these renewable sources out in where the resources are available, whether it's solar in the Southwest or wind in the Midwest. So what you see here essentially is with our existing transmission line, the green line is kind of how far in the available wind resource gets pulled, and the red line, not the dotted one, but the red line that goes up, is essentially the available wind and the cost, or the available cost effective wind that you have with new transmission built. So essentially, even though the wind is there, the real proposition is that we need to move it or we can't take advantage of it at all. And same goes with centralized solar in the Southwest. So the big question and the big challenge and really the big opportunity from the energy sector today with regard to climate change, with regard to carbon reductions, is how are we going to balance the grid? We know that we're going to have plug-in electric vehicles. We know that we're going to have new renewables. We know that we're going to have smart grid. How are we going to balance all of these new resources and all of these new demands on the grid in a way that's going to allow us to, whenever we go home, turn the lights on and have it work? So that's the challenge and the question I would pose to you. And with that, I thank you for your time.
Okay, thank you, Todd. Now listen, I myself have a couple of questions, but I wanted to open up the floor to anyone else who had some, and I'm hoping and I'm counting on some of you guys to have some things to ask. I'm going to take this over here, these guys to hold. Raise your hand if you've got a question. How many people have questions? I see at least 3 hands here. All right. This goes here. It's for the camera. If you can stand up and talk really loud. Anna. Oh, you couldn't hear me. Oh, sorry. Did anybody hear what I just said? calling for questions.
Yeah,
Would you stand and identify which person you'd like to answer it? You know, I'll hand this to you guys to pass.
Okay.
You were talking about when the time that the grid is down, turned on and off. The time between the problem with the grid being down, turning on and off. You're saying could you explain that real quick again?
Between the variability of the wind.
Yeah.
So essentially, I can flip the slide back, but essentially what it's showing is the demand for energy, and particularly electricity, is greatest during the day when we're all using it, because when we're sleeping, obviously we're not using as much electricity, but it's also due to the air conditioning and other industrial systems that are running during the day. And wind, in particular, its variability is typical in that wind blows the hardest at night and slows down the most during the day. So we're making the most wind energy when we need it the least. So that becomes the problem, not just in the fact that we're able to create less wind energy when we have the highest demand, but also because as our demand is ramping up in the morning, our demand for electricity and our energy use, our wind generation is actually ramping down. So we need to kind of double compensate for the fact that we're losing this wind off the grid.
So you were just wondering, the question is, what would we use to counteract that during that time?
Yeah, that's the challenge. So essentially, there's two major opportunities are energy storage, if we can get to scale, get that at grid scale, and then also creating, they're called peaker plants, but typically natural gas powered plants that you're able to cycle on and off quickly when you need to.
I looked at those slides and I saw a very obvious solution. We should all move to Kansas, and we should sleep during the day and work at night.
Why haven't you considered like using solar in the daytime and wind at night?
That is a consideration. Where both resources are available, we're looking into that. That's absolutely. And this is from kind of the U.S. scale perspective and the macro perspective. So there are fewer places where that makes sense from a utility perspective. On a distributed perspective, that makes a lot of sense. But again, this is kind of taking that grid perspective. So distributed generation looks more like a lower demand because you're essentially using your own electricity before you're taking it from the grid.
There's a woman in the back.
Oh yeah, I actually had a question for both Travis.
Mhm.
I was wondering, with your regional plan regarding climate change and that sort of thing, have you taken into consideration freshwater security?
Freshwater what?
Security.
Like water security, water supply.
Yes, I just gave you the component of it that deals with sea level rise. An overall strategy has to take in both fresh water, the supply of fresh water, and it was mentioned that we're going to have considerably less snowpack. It looks like we're going to have about the same amount of precipitation in California, but much more of it is going to be falling as rain and less as snow. We have an entire delivery system that is built around the fact that the Sierra snowpack is a free reservoir. It collects the precipitation, it slowly melts off, we collect it in reservoirs, and then we ship it, and the rainfall, the precipitation is as irrational as the wind. It's blowing at the wrong place from where we are. In California, most of the precipitation is in the east and the north. The people are along the coast and in the south. So we then take all that water, collect it, and move it during the dry season to where the people are. With the precipitation falling as rain instead of as snow, we're going to have to use those reservoirs for flood protection. So as soon as it rains, you fill up the reservoir, then you slowly drain it and you wait for the next storm. And you do that all winter long, except for the last storm. That one you collect it and then you move it. Now the problem is trying to figure out when the last storm is, because if you get it wrong, you either have filled a reservoir and then you have a big storm and you're going to have a flood, or you've emptied the reservoir and you don't have another storm and you don't have any water. So